the simplest analogy here that you can think of. So the scalability of, basically you would have these two different worlds, right? You would have the main chain, which keeps on working, keeps on having the same scalability as it does now, except you would also have this new world that gets created, right? And you can try to represent how much computing power one single node has, right? So remember, we hate master nodes, and so we want Ethereum to processed by a consumer laptop. So on the main chain, the scalability is OFC because every transaction in every block actually has to be processed by a full node, and a full node has to be able to run on one of these. Now, in the new shards, you might notice, which is part of the main chain, proportional to the amount to be able to process at least the correlations on some shard that it cares about, right? So the capacity of each individual shard is also limited to OFC. So the capacity of the number of shards is proportional to the computing power of one node, and the amounts that can be processed by each shard is proportional to the computing power of one node. And so the capacity of the whole thing is OFC squared. Goes up quadratically with the computing power of one node. Now, there are ways to make sharding systems that go up to OFC cubed, OFC to the 4, and potentially O of, like 2 to the power of C divided by some constant, which is like the holy grail, but we're not going to talk about this here yet. And in fact, if we want to go that far, then that would probably be more Ethereum 3.0 territory, which would involve fancy stuff like stars. So that's scalability. Consensus. Now, consensus on the main chain is proof of work now, and it's slowly moving toward proof of stake. In the shards, the consensus for the shards, so first it is going to be basically proof of stake as mediated by the validator manager contract, which sits on the main chain. So basically it's this kind of indirect second layer consensus algorithm that sits on top of the existing main chain. Governance. So the main chain will continue to be governed by hard forks, which are like the best possible way to govern protocol changes because they give users choice, right, Vlad? Okay. And the new shards are basically governed by kind of Ether voting through a validator manager contract, and basically this plus, of course, the users of the shards would also have to download updates in order to accept them. So it's like it gives the users in the shard this is all in the early stages of the sharding system, right? Basically, the roadmap would be that we would start off by releasing this kind of minimal version of sharding, then add two-way convertibility of Ether. Then eventually we would reorganize the system so the shards would kind of be in a more logical position in the main chain. Basically, they would be uncles instead of being transactions. And then the fourth step would be something called tight coupling. And tight coupling is where we say, basically we kind of, the community officially says and agrees, and everyone downloads, clients that enforce that if a given blockchain contains a shard header which is invalid, then the blockchain as a whole becomes invalid. So basically, tight coupling is where the validity of layer 2 becomes a necessary condition for the validity of layer 1. And once you have tight coupling, then basically the entire sharding system would have kind of the same uniform level of security, and it would all basically be governed by hard forks and not really any kind of ETH voting mechanism. So this is what it would kind of in the medium term turn into. And of course, over time, the sharding mechanism would continue being developed and improved. Eventually, there would be new sharding designs. Eventually, there would be Ethereum 3.0 that adds Starks, that adds multi-layer added and bolted on over time. So the way that, and you would also run a kind of sharded chain node. And the sharded chain node would connect to your Ethereum node by RPC, and it would also talk over its own peer-to-peer network in order to broadcast things like shard transactions, shard blocks, and shard collations, and so forth. So it would start off with this kind of separation of concerns, and then, of course, over time, eventually the two would, once we move toward tight coupling, the two would kind of merge together. The is that this gives us an opportunity to do a bunch of important kind of innovation and a lot of important and much needed but backwards incompatible improvements to the protocol by basically turning on those improvements only inside of the shards. Now, of course, at some point the main chain would needs to be upgraded, but we can basically figure out how to do that later. Like, there's no need to have a backwards compatible upgrade mechanism for the main chain be something that slows down access to the sharding mechanism for newly created applications. So, do what? No. So the shard nodes might be subscribing to different shards. So you might be in general, right? Unless you're actually running a data center, your shard node would not be able to fully subscribe to every shard simultaneously. So you would generally have to choose, one to a few shards to subscribe to, and then for every other shard, you would basically be a light client. That depends. So when I give you my Ether address, the Ether address would say what shard. And then for every other shard, you would basically be a light client. So now some of the changes here include things like switching from hexary Merkle trees to binary Merkle trees. This makes Merkle proofs 4 times more efficient. Faster EVM. We could basically go straight into something like EMOS. More parallelizability. There's like 5 different ways to use Ethereum virtual machines. You don't have to